Yes. So thanks for being here on time. I know many people are not here on time, and everybody should be here on time. So I congratulate you for being here on time. I know it's difficult sometimes, but okay. So Misha is going to give his third lecture on cosmology. So Misha, please.
Thank you very much. Good morning. You hear me well? Yes. Okay. Okay, so last time we discussed applications of Big Bang cosmology to several things, such as cosmic microwave background. We found the decoupling temperature of cosmic microwave background. We discussed relic neutrinos, and we also discussed qualitatively nuclear synthesis. Okay, and so that all this type of consideration led us to understanding that okay, that the universe is puzzling. It contains baryonic matter, and it contains dark matter because abundance of matter in total is greater than baryonic matter. And so what we are going to do today, we are going to discuss abundance of baryonic matter, and we're also going to discuss what we know about dark matter. Okay, so that's the plan for today. Okay, so today there will be also my talk, I guess, later on, right? So you will get baryogenesis 2 times, but I'll try to make it complementary in the sense that you're not going to hear one and the same thing all the time. Okay, so we did see that there is an important parameter in cosmology which we were taking from observations. We call this parameter eta, and this parameter eta was a ratio of baryon density to photon density. And empirically, from observations, this parameter is around 10 to the minus 10. Okay? So let's try to understand this parameter better, and let's relate it to something else which we can see in the early cosmology. Okay, and we will do that in the following way. Let's consider this quantity, a number of baryons minus number of antibaryons, and multiply it by the volume of the universe. Imagine for a second that the universe is closed. Okay, so then this combination is just giving you the total baryon number of the universe. Okay, and if a baryon number is conserved, and we do know that baryon number is conserved with high accuracy. The lifetime of proton, for instance, is greater than 10 to the 32 years. So this combination is a conserved number, okay? At least at sufficiently small temperatures. Also, when we discussed hot universe, we know that the entropy is conserved. So if you take the entropy of the universe, number of degrees of freedom times temperature to the cube times volume, so this guy is also a constant. And so we conclude from here that this ratio, baryon density minus antibaryon density divided by total entropy, is constant and is time independent. Okay? So we can do a computation of this ratio. How do we do this computation? This ratio, we can take it today. Today, there are no antibaryons. I will discuss also that later. So we have here just the concentration of baryons. Here is the entropy today, entropy today we can now compute because entropy today is hidden in relic photons. We know what is their temperature. And also part of entropy is hidden in neutrinos. And yesterday we computed temperature of this neutrinos, so we know what the total entropy is. And so we find that this guy is of the order of our parameter eta. It's of the order of 10 to the minus 10. Okay, so now let's take a higher temperature. And for this temperature, I will take 130 GeV. We will see later why this is an interesting number to consider. So if you take this temperature, then we can again compute the entropy because we know what is the number of degrees of freedom of the standard model. It's about 100. We also know the number of quark degrees of freedom. And what we can do, we can express the entropy through this combination. So there is some number in front, counting the number associated with counting the number of quarks and anti-quarks, and total number of degrees of freedom in the standard model. And so we can write this entropy in this way. Okay? And so what does it give to us? That gives us the estimate of baryon asymmetry. Okay? So what you do, you take NB minus NITB upstairs. At this temperature, entropy is given to this number, and so we compute what one would call asymmetry. And then this asymmetry we find is, again, 10 to the minus 10. It's of the order of this baryon to baryon to photon ratio. Okay, so basically this parameter NB over N gamma up to some factor which we can compute is baryon asymmetry of the universe at the early time. Okay, so if you now look at this ratio and ask ourselves how it depends on time, then it has already a non-trivial dependence on time, right? So today it's equal to 1. Why so? Because this guy and this guy goes away. We get 1, whereas at large temperatures is 2, 10 to the minus 10. Okay, and this is the plot of dependence. This is time. This is asymmetry. At earlier time, this is 10 to the minus 10. Today it's 1, and then this curve somehow interpolate between these two extreme values. Okay, and when the transition happen, okay, it should happen at temperatures of the order of hundreds of MeV, tens of MeV. So from where the scale is appearing, this scale is appearing just from the mass of the proton. So we understand what is going to happen. So here you have a plasma with a lot of quarks, anti-quarks, or nucleons and anti-nucleons. Then this plasma, and this plasma has very, very small asymmetry of the order of 10 to the minus 10. Then the universe is cooling down, and you have, say, pair of proton and antiproton. This pair will annihilate and produce to you photons, neutrinos, and stuff like that. And then a small fraction of baryons, which cannot find a pair, stays. Okay, and of course, it's important that something stays, because what stays from this, everything is organized. Okay, galaxies, stars, etc. Okay, so we can ask the question from where all this is coming from, and I will come to that. But there is also an experimental question. So are we sure that this is all true? Okay. So maybe it's just we have baryon asymmetry here nearby us in solar system. Maybe there is also something else far away from each other. Okay, so let's look at that. And let's consider several options. So one of the first options would be that since we said that visible part of the universe is homogeneous and isotropic, and so this baryon asymmetry is global. Whatever place in the universe we find, then we will get an excess of baryons, antibaryons. Okay? So then the question becomes quantitative. So suppose that this is true, but what would be the amount of antimatter in the universe? So we have this asymmetry, but maybe there are some antibaryons floating around. How we can understand how many antibaryons and antimatter is floating around? So there are several methods, experimental. So first, we can search for antimatter in cosmic rays, right? So the Earth is bombarded by cosmic rays, which are coming from different parts of the universe. And we can ask ourselves, are there any antimatter particles coming far away? Yet another question which we can ask is that if there were antimatter in the universe, at some moments, this antimatter particle will meet matter, protons will meet antiproton, and then annihilation will take place. And if there is some fraction of antimatter in the universe, we should see the results of annihilation of matter and antimatter. So you can study that experimentally. So for instance, one of the experiments which produced different constraints, or that is AMS, alpha magnetic spectrometer in space. And so what this experiment is searching for is searching in particular for antimatter in the universe. Okay, so there are above atmosphere, there are cosmic rays coming, and then since this magnetic spectrometer, it can distinguish the particles with positive and negative charges, and so you can figure out how many antimatter particles are appearing. Okay, so this experiment does see antiprotons. The amount of antiprotons is consistent with what you would expect. So antiprotons can originate simply, they can be created in collision of matter particles. Okay, you have proton-proton colliding, and then you can get. Yeah, this is an AMS experiment, which is on space station. It's always. Well, it's working already for many, many years, and it produces, it publishes the result from time to time. So this is a working experiment. Okay, so it gives a constraint, upper bound, on the fraction of matter in interstellar medium, which is of the order of 10 to the minus 6. So you can say that at least we have 6 orders of magnitude more of baryons than antibaryons. There are also bounds from annihilations. So as I said, that if you have antiprotons around, then they will meet protons at some stage. Proton-antiproton annihilation would produce a bunch of pi mesons, and well, and at the end of the day, you will get gamma quanta with a spectrum which you can compute, and then you can look for this type of spectrum. Okay, the average energy of gamma quanta in this case will be around 100 MeV. So this gives to us even stronger constraints on the presence of antimatter in interstellar medium. And then this fraction is about 10 to the minus 15. Okay, so if you have antiproton, which goes around nearby us, then the lifetime of this antiproton would be just about 300 years. So in 300 years, it will meet some proton and annihilate. So if you consider more far away places and look at intergalactic medium, then the constraints are somewhat weaker, but still are very strong. So they're telling you that the fraction of antimatter is at the level of 10 to the minus 6 of that of the matter. And that comes from different astronomical observations. So the conclusion here that if we assume that the universe is really homogeneous and isotropic in all quantities, such as baryon number, then we experimentally we are sure that we have more matter than antimatter, and the amount of antimatter is orders and orders of magnitude smaller than the amount of matter. So this is a solid result. Another possibility is that no, this is maybe universe is homogeneous and isotropic, but maybe in fact this our universe doesn't contain any baryon asymmetry. Maybe there is baryon asymmetry here, anti-baryon asymmetry far away from us, and maybe this is the case. Maybe our structure is that you have some matter here, some antimatter here. Here you have void, nothing, okay? You want to have void because you don't want matter and antimatter touches each other, because if it touches each other, then it will produce the other particles such as photons, okay? And then you can take this type of picture and try to understand what should be the typical sizes of all these structures that it doesn't contradict to observations. And here is the picture from Cohen, Doruchala, and Glashow work, who analyzed this possibility, 50% of baryons, 50% of antibaryons. And this picture shows the following. So this axis here is the energy of photons, and this axis here is the flux of the photons, okay? And these are experimental points which are derived from different observations. And these are theoretical curves. So if you say that, say, the size of these domains is about 20 megaparsec, then you will get this, okay? And so the prediction would be that you have a huge flux of photons, which is much, much higher than experimental observations. Now, if you increase the size of your domains, then theory prediction goes down, which is kind of obvious because the larger is the size. I mean, make the size larger than the size of the universe, then you don't care if there is any antimatter behind the horizon, okay? And kind of the curve, which would more or less fit this observation, would correspond to the size of the domain, which is huge, which is about 1,000 megaparsecs, which is still smaller than the universe size, but really macroscopical. Okay, but this type of analysis, it didn't take into account cosmic microwave background. Okay, and now if you think about the isotropy and homogeneity isotropy of cosmic microwave background, then this picture would be also in trouble. Why so? Because here you need to have voids, zero concentration, and that means that you have very large density perturbations. So I don't know if anybody really did this precise analysis to make a constraints coming from inhomogeneities, but it's clear that this type of patchwork universe, if possible, will contain the objects of the order of the universe size, okay? Which would be also a puzzle. How did it happen that we have a huge space of the universe occupied by matter and another huge space of universe occupied by antimatter? How did it happen? So the question would be even more complicated than to explain the baryon asymmetry of the universe, which is homogeneously distributed over the over the space. Okay, so the remaining possibility would be that you have matter almost everywhere, and there are small pieces of antimatter in one or another place. Okay, and then this small pieces of antimatter could be some anti-stars, for instance. Okay, and there are even papers. Well, there are astronomical observations which say that, well, maybe there are even anti-stars in our galaxy. Yeah, this is the reference to the people. There are also kind of interesting claims from AMS collaborations which are not published. Okay, so the spokesman of this collaboration, he Tink, okay, so he is well giving talks and I mean, say in 2018-21, he announced that, okay, what we found in our observations, we found anti-helium 4, okay? So if you find the anti-helium 4, then that would most probably mean that there are, say, anti-stars and there is antimatter in the universe. So why so? If you have a collision of simple states such as proton and proton, in this collision you will be able to create antiproton, perhaps antideuterium. But to create anti-helium 4, the probability of that is very, very small, right? Because in order to create anti-helium 4, you should be able to create 2 antiprotons, 2 antineutrons, and to create them in a way that they are parallel to each other, so they have time to get anti-helium 4. So the probability of this process is very, very small. And so if you will find anti-heavy element, that there should be a way to make this element. How do you make it? Or in the early universe, or in stellar evolution. Okay, so he has this type of claims that he found few anti-helium 4, but none of these results were published. Okay, so. So this is the evidence, and I would think that this is a strong evidence for really global asymmetry of baryons, antibaryons. Okay, and even if you have this patch scale, patch type universe with matter in some place, antimatter in some place, very, very macroscopic. So in these both cases, we would like to understand why did it happen. Okay? We already discussed the possibility that maybe that was initial condition, so I would find this unlikely. So we, as particle physicists, okay, we would like to see if we can understand this abundance of matter over antimatter in the early universe. Okay, we have this tool, Big Bang Cosmology. Okay, and there are several theory questions. Why at all we have excess of matter and antimatter, and if we are more ambitious, we want to understand this number, 10 to the minus 10. And I think that you will hear what I'm going to say now several times during this call. So I will go relatively quickly through this part. And I'm going to stay mainly on qualitative level, and we will learn much more details, I guess, next week. Okay, so the first proposal to understand why we have more baryons over antibaryons, it came from Sakharov back in '67, and he said, okay, this comes because baryon number is not conserved, but it should be consistent with stability of matter. And this was most non-trivial assumption which he put forward at that time because everybody believed that baryon number is conserved. Okay. Then he said that this is needed because what else is needed is departure from thermal equilibrium. He called that error of time. We can now understand very well why this condition is necessary. If you have thermal equilibrium, just use the thermodynamic formulas. Thermodynamic formulas would tell you that concentration of baryons and antibaryons is the same because masses of baryons and antibaryons are the same as a consequence of CPT theory. And finally, we need the breaking of C and CP symmetries. Why do we need that? We need that because if C or CP symmetries were intact, there is a transformation which changes nucleons to anti-nucleons. There is no difference between them, and then all reactions with particles and antiparticles have the same probabilities.
About the second point, we have already considered deviations from thermal equilibrium, not when you consider, for example, Boltzmann equations, because we know that if we consider only equilibrium, we cannot have enough abundance of light elements or anything. So the second point has already appear in the lambda CDM model, or is other kind of get out?
No, it is already. It is already. So
okay.
Once you have universe expansion, you do have deviation from thermal equilibrium. And from this point of view, the second point is realized in any event. Okay. So, but the importance of this point is the following. At the end of the day, we not only want to understand why we have more baryons than antibaryons, we also want to understand the number. Okay, and everything, all the statements here, they are can be quantified in a sense. Okay, I have baryon number non-conservation. Okay, if this baryon number non-conservation is extremely weak, then presumably it will not lead to to any baryon asymmetry, or if deviations from thermal equilibrium are minuscule, very small, then you also don't care. You see, so we need, there is some quantitative measures of all these things.
You wrote that deviations from thermal equilibrium provide you an error of time. But CP violation also means T violation if you assume CPT. So this also provides you an error of time at the level of single bodies.
Okay.
So,
Yeah, so
isn't CP violation enough?
Okay. So indeed, once you have CP violation, and if CPT theorem is true, let's take it for granted, that means that there is error of time, there is a T violation as well. Okay, now, if you have just this source of T violation, and if you don't have deviation from thermal equilibrium, you will get 0. Because here CPT is superior to all that. So if you have thermal equilibrium, let's forget about universe expansion and just look at that from academical point of view. Suppose that we have some theory which breaks baryon number, which breaks C and CP, but still there is CPT conservation. Then CPT conservation will guarantee to you that the number of baryons and antibaryons are the same. So you need really this, these 3 conditions for theory to work. Yes.
Sorry. So recently, I think in the past year or so, there was some papers that claim that they could find some kind of parity-breaking signal in the large-scale structure of the universe. And of course, it's not directly linked to this problem, but could it be the case that if we detected some kind of parity violation in the large-scale distribution, we could go back to that case, or where we have some kind of asymmetry between our universe and some, and could this explain the baryonic asymmetry?
Okay. So indeed, there were indications in the literature telling that there may be a parity violation in several cosmological observations. Okay. It's not easy to explain that theoretically, okay, and if this is indeed true, this is indeed true, these observations, that would require certainly reanalysis of the early universe, and there could be a relationship to baryon asymmetry.
Yeah, I mean, I know
this is this is the case. So I will put it in the following way. So if these observations are true, then they signal about non-consistency of lambda CDM, for instance. Okay, and once you have any type of inconsistency from this standard cosmological model, that would be an indication of new physics. So for instance, if you look at kind of, let's call it standard inflationary paradigm or different scenarios for baryogenesis, they don't produce that.
Absolutely. Okay, yeah. Thanks.
Okay, so we need all this, and the first question which would arise in this enterprise is whether we can get baryon asymmetry of the universe in the standard model of elementary particles. Okay, that's what we should start with. We know that this model is experimentally confirmed. We should try it to explain baryon asymmetry. And kind of amazingly, it happens that on qualitative level, all these three conditions in the standard model are satisfied. And so let me go through them again relatively quickly and on a qualitative level, because I'm sure you will hear more discussion of these points next week. Okay, so you have lectures by Gustavo of the standard model, okay? And if you take perturbative standard model, then in perturbative standard model, you find out that there are 4 globally conserved numbers. Okay? And these are the numbers of electron plus electron neutrino. We can call it electron lepton number, then muon lepton number, tau lepton number, and baryon number. And so if you plot whatever Feynman diagram in electroweak theory, in the standard model, you will see that all these numbers are conserved. Okay. However, it happens that there is a non-perturbative effect which breaks these numbers. And so at the end of the day, only 3 of them are conserved. And these 3 are these combinations, number of electrons minus 1/3 baryon number, the same for muon, same for tau, whereas the B plus L is not equal to 0. Okay, so what I will tell you now is how we can potentially understand this just drawing different pictures, okay, without doing computations. So for doing so, I remind you the story associated with Dirac equation, right? So Dirac invented his equation a long time ago. And the trouble with this equation, initial trouble with this equation was that the solution of Dirac equation gave you the states with positive and negative energies. Okay? So if you look at here, this is, say, velocity of the particle or momentum, then you have one branch which well describes electrons, and then there is a negative branch which first Dirac thought that it should describe protons, but then it was pointed out that this cannot be the case because these guys have the same masses. And so to save the situation, Dirac invented a picture which is called Dirac vacuum. Okay? And so this picture, from contemporary point of view, is very misleading. Okay, because if you try to apply this picture to bosons, you will get nonsense. But anyway, this is a qualitative picture which leads to correct results in condensed matter physics in many cases, and it's kind of important. And the picture was the following. So he said that, okay, fine, we have this negative branch, but we want to describe fermions, okay? And fermions, they obey Pauli exclusion principle. And so let's construct our vacuum in the following way. All negative energy states, which you have here, we are going to fill, okay? And so if this all negative states are filled, then our system is stable. Why? Because any particle with positive energy cannot decrease its energy because all negative energy levels are occupied, and Fermi exclusion principle doesn't allow you for this type of transition. Okay? And this picture gives you immediately a lot of benefits. So it tells you that there is an excitation like particles. So this is an electron. But there are also antiparticle excitations. So what you do, you take this branch, which is called Dirac C. You make a hole here, okay? And then the energy of this state with the hole is in fact positive, and the electric charge of this state is opposite to that of electron, okay? And so you come with this picture, and then you predict the electron. So Dirac predicted electron in this way. And then say the picture in which you create an electron-positron pair is like that. You take, say, a photon, and then this photon does something, and it takes away this field state, put it in the energy, positive energy branch, and at the end of the day, you have electron and positron. Okay, so that's a great picture. And it happens that if you use this notion of Dirac-C, then in electroweak theory, there is yet another process which is not described by the previous jumping. Okay, and this process is demonstrated here. Say that this axis is time, and this axis is the energy of fermion in the Standard Model. So you start from a vacuum state. Vacuum state means that all negative energy levels are occupied. And then you do something with your fields, with the Higgs field, with W and Z fields. You modify them in some peculiar way, and you follow what happens with the energy levels. Okay, and then you see this picture, that one of the energy levels, this one crosses zero, and at the end of the day, you have this one particle. Okay, not a pair of particles, but one particle. Okay, so this is a typical example of infinite number hotel, right? You come to the hotel, receptionist told you all rooms are occupied. You cannot get in. I'm sorry. So you tell, oh, don't worry. Take every customer, put it in room N from N to N plus 1, and you will get a room for me. And so that's exactly the process which is happening in the Standard Model. Okay, so in order to create this type of thing, it happens that you have to create some combination of W and Z and Higgses, which has some energy, okay? And so in order to go from this state to that state, you have to overcome some barrier. This barrier happens to be of the order of 10 TeV. It's parametrically MW over alpha, so you see alpha downstairs, and that shows to you that this process is non-perturbative. And then you can tunnel through this barrier, and then this process happened. Okay, so that's what 't Hooft first discovered. The selection rules for this process in the Standard Model are kind of peculiar. You have 12 fermion doublets in the Standard Model. You have to account for color there. And you have to take one fermion from every fermionic doublet for this to happen. So when you change the gauge field, etc., so this picture, it happens with every fermionic doublet. So this process creates 12 particles in total. Okay. The proton is stable because it contains just 3 quarks. Okay. And the lowest process in which baryon number non-conservation happens in the Standard Model is, for instance, this one. You take the deuterium, and the deuterium can decay into antineutron and 3 leptons. Okay. You can compute the probability of this process. You find that at 0 temperatures, this is negligibly small. At finite temperature, the rate is enhanced. You're getting some Boltzmann suppression. You have to overcome this barrier. Okay, so you get exponential minus m sphaleron. Sphaleron is 10 TeV divided by temperature. And if you take temperatures even higher, then you have a suppression, but then this is a suppression by the fine structure constant of SU2. Okay, and you can take that, you can plug it into cosmology, you can compute, since this is the rate, you compare this rate with the Hubble rate, or this rate with the Hubble rate, and then you find that the baryon number non-conservation in the standard model is kind of perfect for baryogenesis, because it's in thermal equilibrium about 130 GeV, and at small temperatures is so weak that it doesn't lead to the instability of matter. Okay, so here we are fine. It looks like, yeah, we can take standard model and get baryon asymmetry. Okay, another part is CP violation. I don't know if Gustavo already described CP violation in the standard model, not. Okay, and then I will tell you a few things. So standard model, there is CP violation, and this CP violation is associated with so-called CKM phase. It's Kabiba, Kobayashi, Moskova phase, okay? And, but there is a very, very peculiar feature of CP violation in the standard model. If you say that the masses of two masses of op quarks are degenerate, or the masses of down-type quark are degenerate, then CP violation in the standard model can be rotated away. Okay? Why this fact is essential? It's essential because you can, once you accept that, it can be derived pretty easily. But once you accept that, you can find immediately, without big work, the measure of CP violation in the standard model at high temperatures. What you do, you say, oh, okay, if, say, mass of T is equal to mass of U, then CP violation must go away, and therefore the measure of CP violation must contain the product of all these 6 factors. Okay? You cannot put mass to the first power because mass never comes in the first power for fermion fields, right? You change the mass of fermion field in any Lagrangian that doesn't lead to any effect, right? You can do a transformation of phase in Dirac equation which changes plus to minus here. Therefore, all these guys must come into square. So you put all that. Then there are different phases appearing in the mixing between the quarks of different generations. So the measure of CP violation must be such. This is dimensional full quantity. We are interested about this CP violation at high temperatures. These high temperatures are about 130 GeV, right? Because if we are below, we don't care, because Svaleron processes are switched off. So you put this combination together, you get 10 to the minus 20. Okay, but baryon asymmetry, if you compute it, perhaps this is very complicated computation, but it should be proportional to the measure of CP violation. The measure is 10 to the minus 20. You want to get 10 to the minus 10. Okay, it doesn't work. Now, deviations from thermal equilibrium. We are talking about the processes occurring at 130 GeV. We know very well what the standard model is. Okay, we can compute all processes in the standard model at this temperature, compare it with the rate of universe expansion. We find that, say, strongly interacting particles are very well in thermal equilibrium. Weakly interacting particles are very well in thermal equilibrium. you should get an extra suppression. Okay, so you can kill standard model baryogenesis twice if you want, one from this part, another from this part. There were many attempts done to overcome that, and they were unsuccessful. Attempts by myself as well. I tried to make it, it didn't work. Okay, so this tells us that we cannot explain baryon asymmetry within the standard model. And that's an important statement, because it tells us that the standard model should be extended. There should be some new physics beyond the standard model. Okay. There are different approaches to that, and I will shortly go through two of them. One of them is baryogenesis via leptogenesis. There will be lectures about that. And then bubble wall electroweak baryogenesis. And again, there will be lectures about that. So I will just discuss qualitative features. So the first one is associated with extension of the standard model in neutrino sector, and new particles which are introduced there are called heavy neutral leptons. And in this case, new particles which are added to the standard model are Higgses and new fermions. And here departure from thermal equilibrium is associated with first order phase transition, what Mikko Laine is discussing in his lectures. Okay, so baryogenesis via leptogenesis, it's based on the following idea. You take the structure of the standard model. So this is the structure of the standard model, which you learned here at these lectures. Peculiar feature here is that there are no right-handed partners of neutrinos, which leads to zero neutrino masses. And so let's add, let's fill these boxes and get a model which has right-handed neutrinos. So this theory happens to be very interesting. It's called the type 1 seesaw model, or new MSM, neutrino minimal standard model. And this theory explains neutrino masses, so everything is fine with neutrinos. This theory provides an explanation of baryon asymmetry. It also gives dark matter candidate sterile neutrino, which I will discuss later. What do you do in this theory? You know very well the Lagrangian of the standard model, and now you modify it. How do you modify it? You add these right-handed particles. Okay, they're singlets with respect to the standard model group. So they may have Yukawa interactions, and also in addition, they have Majorana masses. Why? Because they are singlets with respect to SU2 cross SU3 cross U1, and this mass term is allowed. And this term, it breaks lepton number. Okay, that's important. And once you have this Lagrangian, from the point of view of baryogenesis, you get a lot of benefits in comparison with the standard model. So you get new particles. You get new sources of CP violation, which are sitting in these Yukawa couplings. Okay? So in the standard model, there is just one source of CP violation, which is CKM mixing phase. And here, this complex Yukawa couplings, they introduce a lot more. And also, since there is this term here, then this term leads to violation of lepton number. And so as a result, this theory, it doesn't have any global conservation numbers whatsoever. So everything is broken. Baryon number is broken by anomaly. As I discussed, lepton numbers are broken because of this mass term. Okay, and then you go ahead, you take this theory, and you compute baryon asymmetry. Okay. There are different reactions. So for instance, these new particles can decay into lepton and Higgs, anti-lepton, anti-Higgs. There are different scattering processes, and all these reactions, they occur with CP breaking, because there is a lot of CP violation in this theory. And then what happens in all these reactions is that you may produce lepton asymmetry at the first step. At the second step, sphelerons can convert lepton asymmetry into baryon asymmetry. Okay? And so the generation of lepton asymmetry must occur at temperatures above sphelerone freeze out, about 130 GeV, because before that, sphelerone processes are not operative. So this is the whole picture. Okay? If we apply our second Sakharov condition, deviation from thermal equilibrium, then we can imagine two different scenarios. So one scenario is associated with freeze-in, and another scenario associated with freeze-out. So in pictures, this looks as follows. If this is time, and this is the ratio of number of these new particles to the number of photons. So these particles, they interact very weakly with everything, and so initially their concentration before they come into thermal equilibrium are much small, then they come into thermal equilibrium, and then they disappear because they decay. And then there is this important line, which is the line of sphelerone freeze-out. Okay? And this line of sphelerone freeze-out, if you put it here, when there is equilibrium, then nothing is going to happen, because every processes are in thermal equilibrium, and baryon asymmetry will not be generated. So we can put this line here or there. In this case, we get generation of lepton asymmetry at freeze-out, and in this, here we get generation of baryon asymmetry at freeze-in, and here we get generation of baryon asymmetry at freeze-out. And I'm going to leave all the details of all computations and tell you what the result is. If this is the mass of these particles, and this is the strength of the interaction with the rest of the matter, then in this domain, you can explain everything. You can explain baryon asymmetry of the universe, and you can explain all neutrino masses. So this domain corresponds to sufficiently strong interactions, and if interactions are sufficiently strong, then here particles come into thermal equilibrium, they equilibrate. Second Sakharov condition is not satisfied, and then there is no baryogenesis. Okay, so basically the message is that this works, okay, and if the masses of these particles are sufficiently small, then this hypothesis can be even tested experimentally in future experiments. Okay. Are there any questions at this stage? Because I will now come to another possibility.
This kind of lepton or baryonic number breaking is for a specific flavor, or it must be equal to all kinds?
These are all kinds.
Okay.
These are all kinds because all different fermionic families, they interact in the same way with W and Higgses. Okay, and so if you make a change of W and Higgses in a particular way, then all fermionic generations follow that. So your question was about sphalerons. Yeah. So this is the uniform.
Is there any hope to measure the lepton asymmetry?
Sorry, any?
Any hope to measure the lepton asymmetry?
Well, there is always a hope. Okay. If there is a lepton asymmetry which is sufficiently large, and large meaning 5-6 orders of magnitude larger than baryon asymmetry, then this type of symmetry start to influence on different processes in the early universe, such as Big Bang nucleosynthesis. Okay, so if there is lepton asymmetry, which is large, that can change the helium-4, say, concentration. Okay, so from here we can get some bounds. So whatever deviation, say, from standard BBN you may find, you can try to associate that, for instance, with lepton asymmetry. But experimentally measure this asymmetry would be difficult because of the following reason. At high temperatures, this asymmetry would be distributed between charged leptons and neutrinos. But when the universe cools down, all this lepton asymmetry will be in neutrinos, in relic neutrinos. And it's already difficult to find them. So it's getting complicated.
Yeah, also I think that there is some chance, as you said, in Big Bang nucleosynthesis in the early universe. But nowadays, since for sure two neutrino species are non-relativistic, maybe also the third one, even if it is consistent with zero mass. And then, in fact, this lepton asymmetry in neutrinos is not really a lepton asymmetry, it is a helicity asymmetry. Yeah. And since neutrinos are basically at rest, any asymmetry now is evaporated. Unless you are left with some polarization, some residual. But what I want to say is that for sure there is an additional suppression due to the non-relativistic nature of neutrinos today.
Yes, that's a very good point which Enrico made. Okay, so the point is that if neutrinos are Majorana particles, then it doesn't make sense to tell that the number of particles is greater than the number of antiparticles because they're all Majorana particle coincide with antiparticle. And what is left is their chirality. However, there was a recent paper last year by Oleg Ruchaysky and others who demonstrated that this chirality survives.
I know, it survives an amount of polarization or residual polarization, yes. But it's a very strong suppression on top of measuring, the neutrino background. So I think it's most probably really hopeless.
I think there's a question online. Yeah, I'll just read. For spharon transitions, you mentioned only left-handed quark doublets. Why are right-handed quarks not considered?
The reason is the following. If you look at SU2 part of non-abelian interactions, then only left-handed quarks participate in that. Right-handed quarks, they're all SU2 singlets, and they do not participate in SU2 interactions. So that's the reason why left-handed particles why right-handed particles are not counted in sphalerone transitions.
Okay, more questions? So something maybe for the discussion, because you have to introduce new sources of CP violation in the leptonic sector, and there may be some experiments can detect this CP phase in the leptonic sector. But this is for the discussion.
Okay. Okay, so let me go through other scenario for electroweak baryogenesis, which is associated with phase transitions, what Mika discussed in his lectures. Since he discussed already many things, I will just skip few things, and let's assume that indeed a phase transition in electroweak in the standard model happens. So it cannot happen in the standard model as we know it. It's a continuous crossover. But if the standard model is supplemented by new fields, by new Higgses, etc., we can imagine that the phase transition in the standard model occurs. So how does it go? If this is the order parameter, the scalar field, like Higgs boson, and this is the free energy, then at temperature greater than the critical temperature, the potential has this form. At temperature equal to the critical temperature, these two minima are degenerated, and at temperature below the critical one, this state has a low of free energy. So imagine that the universe was initially here with a small vacuum expectation value. Then the universe expands. Eventually, potential evolves into this picture, and then the phase transition starts. Then this phase transition occurs through the bubble nucleation. You get bubbles of a new phase with a large vacuum expectation value of the scalar field inside, and here you have a symmetric phase. Just an order of magnitude, if we talk about electroweak phase transition, then the size of the bubbles which are nucleated are microscopic, and then this bubble expand and they percolate when they collide at the size of the order of 10 to the minus 6 centimeter, which is a fraction of horizon size at that time. Okay, and then the idea of electroweak baryogenesis is to exploit this picture. And this is how it may happen. Here I plot the same bubble as here. So inside the bubble, we have large vacuum expectation value of the Higgs field. Okay? And inside the bubble, the rate of Sphellaron transitions is suppressed. So inside the bubble, baryon number is conserved. Outside the bubble, vacuum expectation of the scalar field is small, and baryon number is not conserved. And now you have this bubble, and this bubble expands. Okay? And then there are processes occurring with quarks and leptons at the boundary of this bubble. Inside the bubble, our particles get masses from vacuum expectation value. Outside the bubble, the particles are almost massless. So this means that the quarks and antiquarks will be reflected or transmitted inside the bubble. If you have CP violation, then the processes with particles and antiparticles will have different probabilities in general. Okay? And you can imagine that you send here the quark, and you get inside the quark with higher probability than you send here an antiquark and get an antiquark here. So when the bubble expands, this system will separate baryon number from anti-baryon number. Inside the bubble, you will get more quarks. Outside the bubble, you get more antiquarks. And now, inside the bubble, baryon number is conserved, so nothing happens with these quarks. Outside the bubble, baryon number is not conserved, and this mismatch between quarks and anti-quarks disappear. Okay, so this is the idea. And then when the bubble fills the universe, it transforms everything in the state with non-zero baryon asymmetry. Okay, so this is a qualitative description of the process. Now, how you do your computation? You take a theory which embraces the standard model, and you explore this hypothesis. Okay? You should find a theory in which there is a first-order phase transition, which can do this bubbles. Then you should have a theory which has enough CP violation, which can do the separation of baryon number from anti-baryon number for you. This phase transition should be sufficiently strongly first order so that inside the bubble, the baryon number is conserved. Okay, so there are many challenges here, but the answer is positive. You can construct theories in which this idea works. Okay, and there are many other ideas which I'm not going to discuss at all, but they will be discussed in the following lectures. I'm not sure about barogenesis from black holes, but certainly others. Okay. Any questions at this stage?
I have a question about the domain wall. I have a lot of difficulties to see what the domain wall looks like. I mean, in a magnet, I can see what the domain wall is, but here is a field. So the domain wall is what? It's kind of transient of the field?
So you have this type of potential, right? So this is phi, and this is v phi. If this is 0, and this is phi 0, this domain wall is the following configuration. This is x, this is field phi, and then you have here something like that. And here phi 0. Okay, so this is a space-dependent configuration of the scalar field.
I see. Okay, great. Thank you.
My question is on the domain wall too. I wonder about this stability of the domain wall. I mean, what this has to do with stability with our calculation, you know, with the existence for, you know, phases and that.
Okay. The question of stability of domain wall, it can be addressed mathematically in the following way. Okay, for this situation, which I said, this point is more energetically favorable than that one. Okay, so you don't have a plain domain wall in this picture, but you have a spherical domain wall which moves in a particular direction so that the state with phi 0 not equal to 0 is expanding. Okay. Now the question of stability. How do you do that? You take whatever situation you are interested in. Well, this one, or the simplest situation would be at TC, when the domain wall will not be moving and can be plane. You find the solution. Let me write phi classical, which is a function of x and t, and which satisfies the classical equations of motion. And then you consider a perturbed state, delta phi, and you ask yourself what happens with delta phi, whether it oscillates or maybe exponentially expanding. So the answer for all this thing is that all delta phi's are just oscillating so that these configurations are stable classically.
Two more questions.
So I'd like to mix these electroweak with leptogenesis. So you have a bubble in which antimatter enters more, matter enter more than antimatter. And then B is conserved inside the bubble and not conserved outside. But if neutrinos are Majorana, they could enter, get in and get out with the same rate.
Sorry, say it again.
If neutrinos are Majorana,
If what? If?
neutrinos,
Yes.
Majorana, then it's on antiparticles, so it would get in and out of the bubble with the same rate.
You see, neutrinos do not participate in that at all because of the following reason. Neutrinos, well, in this type of theory or in other type of theories, they still have very, very small masses. Okay, and you have a big reflection of quarks and anti-quarks, or maybe other particles, maybe charged leptons, or maybe some other particles, because they interact strongly with the Higgs wave, and their masses are different in different phases, and that leads to reflection. Okay, so if you look at this picture and imagine that you have a particle, some fermion, with the mass m times phi 0. If the energy of this particle is below this height, below this mass, then it will be reflected 100% time. But for neutrinos, this is so small so that they go through without interacting. Okay.
We can discuss this later.
Yeah, we can.
I don't really understand why do we need a first order phase transition. Can't we have, for example, a second order phase transition, and then like we can have regions with, in the universe where you have with phalerons unsuppressed, and regions where it is suppressed, where like you have waves not equal to 0?
Well, when you have second order phase transition, then the fluctuations of the order parameter phi are small. Okay, and this means that you are not going to get this picture. So here, in order to suppress phalerons, you need to have phi 0 over t greater than 1, so that the jump of the order parameter here should be really large. And for second order phase transition, this doesn't happen.
So I think it's the same from the question from online from Disha. I think, sorry, coming back to my question, I missed why Svaron transition is only due to SU2L and not abelian symmetry hypercharge.
Maybe I can continue and then answer this question at discussion if it's okay.
Yeah. So yeah, I think Misha will discuss this in the discussion session.
Okay, so I want to say something about dark matter, because otherwise I will be really out of schedule. So what I will do in remaining 10 minutes, I will try to cover this part. Okay, without discussing any particle physics candidates. Okay, so we discussed baryon asymmetry of the universe. Okay, and this is why we have omega matter non-equal to 0, but we have also dark matter. We did see that the omega matter, omega non-relativistic matter, is 0.3, okay, which is greater than baryon asymmetry. So how can we detect this dark matter? Okay, imagine that we have some particles which do not interact or interact with everything which we have very, very weakly. Okay, so how can we detect these guys? Yes, we can detect these guys due to gravitational interaction. Okay, so if you have some gravitating body with mass m, and then let's look at some test body. I call it test body. It can be some star which goes around this gravitating body. Okay, then by observing the motion of this test body, we can estimate the mass which is inside. So how can we do that? This is an elementary estimate. If you have a bounded system, then there is a virial theorem which tells you that the potential energy is of the order of kinetic energy. You can put precise coefficient in front. This means that kinetic energy is of the order of that. And okay, this mass cancels. And then you see that if this mass is concentrated at one point, or you have some spherically symmetric distribution of matter, which doesn't touch this point, then the velocity of your test body will depend on the radius as 1 over r. Okay? You cancel this, and you get this 1 over r. Okay, and this v is called rotational velocity, and this rotational velocity, it can be measured in different observations. So if, for instance, if you take our galaxy, so our galaxy, it has this type of structure, so all visible mass is concentrated roughly in some localized place, and if your test body is far away here, you would expect that the velocity of your test body will fall with the distance from this point as 1 over r. Okay? If you do this exercise for the solar system, that's exactly what you are going to observe. If you take different planets, so this is the distance from the sun to the planet, and this is the rotational velocity. If you put here different planets, Mercury, Venus, Earth, whatever, Mars, etc., you plot the theoretical curve, 1 over r, you will find that everything fits greatly. Okay? But this doesn't work for galaxies and for other objects. You have some radius. This is again rotational velocity. This is what you would expect by measuring the known mass here, and this is what you observe. Okay, and this is more artistic picture. This is the distance. This is rotational velocity. That's what you would predict by observing stars and other matter which you see inside, and this is what you measure. Okay, so what does it mean? That means that there is some substance which doesn't shine, which exists in these bodies, and which has a non-trivial density distribution, and this density distribution should scale at large r as 1 over r squared in order to get flat rotational curves. Okay, and so you see that from many observations, and the conclusion which you should make from here is that universe contains some matter which clusters around galactic centers, around clustered centers, which doesn't shine, which is in most cases nearly symmetric. Okay, so in spite of the fact that here you have a spiral galaxy and the disk, whatever the velocity you measure at different points, you find one and the same value, so that this stuff which doesn't shine should be spherically symmetric. And the question arises, what could it be? Okay, so if you talk about protons or neutrinos, which are not combined in stars, then it happens that this cannot be the case. So why protons cannot be the case? Very easily, because we know the number of protons from Big Bang nucleosynthesis, which is smaller than the amount of dark matter we observe. And neutrinos cannot be dark matter candidate because of the reasons I will tell you a little bit later. Okay, and that's not, this rotational curves, which I was talking about, is not the only source of evidence for dark matter. So the observations of cosmic microwave background tell the same. Observations of, we discussed already this plot which shows what is the composition of the universe. Okay, so what I want to discuss are just very generic constraints on the properties of dark matter particles. One of these constraints is applicable for fermions. And let me tell you what is the idea behind this constraint. It's, again, associated with Pauli exclusion principle. Suppose that you have some object in the universe, some dwarf galaxy, or galaxy or whatever, which contains dark matter. Okay? And then you say, okay, these are fermions which make me dark matter, and so I'm going to put the fermions inside. Okay? I cannot put more than one state per, more than one particle per one available state. Okay? And then you simply explore this thing. Okay? And this leads you to a lower bound on the mass of fermionic particle. Okay? Because there is a limited number of particles which you can put inside. You know the size of your object, you know the mass of your object from observations, and you ask yourself, what should be the minimal mass of fermionic particle so that everything fits the data. Okay? You can look at different objects on the sky which are most dense. The most dense objects are dwarf galaxies, okay? And this is the result which you are getting. So neutrino is excluded. Neutrino cannot be a dark matter particle because already from comparing of neutrino, we know how many neutrinos are in the universe. We know that there is an upper bound of neutrino mass which we found, which is, say, 10 electron volt. And here, what is needed is that the mass is must be big enough. So neutrinos are excluded. If we talk about bosons, then there is yet another constraint on the bosons, which is much, much, much weaker than the one I just presented. So if you have bosons, then the Pauli exclusion principle doesn't work, right? You can put as many bosons as you want in this place. And so one of dark matter candidates, which is light, which is axion, it, of course, doesn't satisfy this Tremont-Gunn bound. There is yet another constraint, which is the following. If the mass of bosonic particle is very, very small, then there is a, this particle cannot be concentrated in a very small volume, okay? So it has de Broglie wavelength just from uncertainty principle, okay? And so the constraint is the following. Take the size of the smallest object in the universe which contains dark matter, which would be some dwarf galaxy, and require that the de Broglie wavelength of dark matter particle is not greater than this value. Okay? So that leads you to yet another constraint, which is as weak as 10 to the minus 22 electron volts. And if you have a particle with this type of mass, this goes under the name of fuzzy dark matter. There is yet another generic constraint on dark matter particle, but since I'm running out of time, I think I will postpone this discussion for tomorrow.
So more questions for Sasha, for Misha? Yeah, there's also some online questions, right?
I have two questions. One is, these bounds are made in take the size of the galaxy, right?
They take, well, the last bounds, it just takes the size of the galaxy.
But
nothing
how
else.
can you define the size of a galaxy if it's the size of the halo that we cannot see?
Yeah, no, but what you do is from observations, you look at the rotational curves, right? So you look at rotational curves. So from observations, you know what is the dependence of velocity on the radius, okay? And knowing that, you can reconstruct the density profile, okay? Now, once you reconstruct the density profile, you can ask your question. Suppose that I have a particle, scalar particle with a particular mass. Can this particle, in principle, describe this density profile? Okay? So you are right in the sense that there is no sharp boundary, and this dark matter, you say, okay, the density scales like 1 over r squared, so what is the typical size? Okay, this is a rough estimate, but this estimate can be refined once you know the precise distribution.
Okay, it was clear. My second question is, I ask, can you provide the reference that do these bounds calculations to us?
Sorry,
Can you provide the reference that do this bound calculation to us?
Yeah.
It was
So
nice.
for instance, I can do that at discussion session. I can go in more detail through the Streaman
Thank you.
bound. Yeah, I can do that.
When we study dark matter halos, I picture them as being coplanar with the baryonic matter on the galaxies. But the way you talked, it seemed like it was spherical, and the results were necessary. This was a condition for the results to be achieved, and that isn't very clear to me. Why? How can we be sure they are spherical?
No, it's again the question of measurement. Okay, so you have galaxy. Okay, well, visible part of the galaxy is say disk, and then you can find test bodies which are not necessarily in this disk, but they are in different directions from the bulb of the galaxy. Okay, and then you look at their rotational velocity. And so you can find rotational velocity as a function of the angle, okay? And then these observations telling you that the halo of the galaxy, which contains this dark matter, is nearly spherically symmetric.
Thank you.
Well, that's expected. No way the galaxy is a disk, because baryonic matter dissipates energy, whereas dark matter does not dissipate as much. But we can discuss that.
I think the online question is pretty quick. It said, what is the phi field exactly? Higgs, I believe, probably refer to this phi.
For this part, the answer is that this is not 100% our Higgs field. Why? As Mika explained, I guess to everybody, the standard model doesn't have phase transition, first order phase transition. There is a crossover there. And so to have first order phase transition, the standard model has to be explained, and it has to be extended, and then it has to be extended in the scalar sector as well. So scalar sector is more complicated, and then the first order phase transition, which happens, it incorporates several scalar fields. Okay, and the parameter, order parameter is just not scalar field, but some direction in this complicated scalar sector.
And then the follow-up is just, is there any evidence for phase transitions?
In condensed matter physics, there is plenty of evidence for phase transitions. And you are seeing that every day if you boil the water in a teapot. Yes, there is. But in quantum field theory, no, we don't have experimental evidence. It's very difficult to reproduce the universe in particle physics.
Okay, so I don't see any hands up, so let's thank again Misha. So just a couple of announcements. So there's a colloquium by Misha, so we have a double dose in the afternoon at 2, and the colloquium